can introduce Chris.
Good afternoon, everyone. So, as a MC, traditionally, you need to find a joke to introduce the next speaker. So I did a bit of.
Can you maybe try the other one?
It doesn't work? It does. Okay. Good afternoon, everyone. So traditionally, as a MC, you need to find a joke or like a pun to introduce the speaker. So I did a bit of research, and unfortunately, the CV of Shafi was no jokes. And you know this, Shafi is the recipient of the Turing Award for 2012, and she was also the recipient of not one but two Gödel Prize, and including her contribution for zero knowledge proof, if you're aware of this. And so today, I'm really excited to introduce Shafi, who is also a prof at Berkeley and previous director of the Simons Institute, and she's going to talk about theory of cryptography and AI safety. Thank you.
Hi, everyone, and I'm really sorry for not being there in person. And I even told the organizers that they could probably guilt me into coming back, but I was so exhausted and they were so nice, and I'm not in person. Okay, so the title of my talk, I'm not sure if I gave it or somebody else gave it, is what can theory of cryptography tell us about AI safety? Can you hear me? Yeah?
Yes.
Okay. And I think there are two operative words here that I want to sort of focus on, and one is theory and the other is cryptography. So I'll start just by some sort of slides that I always put in the beginning of a talk about cryptography in the realm of AI, and that is just to make people realize that usually when you talk about cryptography, you can think of it as a bunch of tools, encryption, digital signatures, proofs of work, zero-knowledge proofs, and so forth and so forth. But really, if you zoom out, all of these things essentially enable us to sort of put blind trust in technology, even when we know that adversaries are present. So in other words, we know somebody wants to listen to our messages, someone wants to pretend to be me and get into my bank account, somebody wants to, I don't know, steal my money on a crypto blockchain. That's the assumption. And yet we're saying, don't worry, we've put some cryptographic methods to the rescue. You can pretend like they are not present. So wouldn't it be nice if we could address machine learning questions the same way? Sort of using this kind of a paradigm, and maybe also the tools and the assumptions. And to a large extent, when we talk about cryptography, we really have it down to a recipe, which I don't know if to compliment or not, but it is the fruit of many years of work. And if you think about this recipe in the machine learning world, we could say the machine learning, there's a task, there is step one. Step two, and that's the very important step from a crypto point of view, and I think should be very important also from a machine learning point of view, is let's model the adversary, the machine learning adversary. Then you define what is a good enough solution for you. Say, I call it trustworthy solution, but have a sort of precise math definition of what is good enough. It might not be much, but at least it's precise. Then you build a solution. And finally, the important part, and that's where the theory comes in, is prove rigorously that your solution satisfies your definition of what trustworthy means in the presence of the adversary that you modeled. So that's the cryptographic, recipe. And in the cryptography setting, those tasks might be, again, privacy, encryption, authentication, using digital signatures, and so forth. And when we talk about proofs, we mean mathematical proofs that are rigorous, but the truth is that we make assumptions all the time, but we make them explicit. And the kind of assumptions we do in crypto, under which we can prove these theorems, that let's say a particular solution is good enough, are a variety of kinds, but the only one that I'll talk about today is computational hardness assumption. That is that there are some problems which are too difficult for computers to do in a reasonable amount of time. And the assumption is that, of course, your construction is as strong as your assumption, but we have these problems out there which we don't know how to solve. They've been around for a long time. And the assumption we make is that they're impossible to solve. But it's not just that we assume that the whole solution is impossible to solve. That just our solution is good, but rather it has the sort of this double-edged sword flavor to it, which means that if you could break the solution, if somebody comes around, an adversary, and he can show you that the solution does not satisfy the definition, then that turns into an algorithm for solving the presumably hard problem. So we sort of say, well, either way we win, either we have a good solution or we solve some really difficult mathematical problem. So that's going to be like our wish. Now, sometimes we actually can't solve a problem or we can't satisfy the definition we gave if the adversary is too strong or something like that. And then you could also prove it, that there's nothing to do. You might as well look either modify your definition of what you're after or give up. But also then sometimes our proofs are under a cryptographic assumption. So there are possibility results, there are impossibility results. So let's see if this whole story fits for machine learning and for safety specifically. So I just want to say before we start is that cryptography and machine learning are not the same. So using the same recipe might seem a little dubious to some, because after all, cryptography really is designed for the existence of an adversary, whereas machine learning has a lot of payloads that have nothing to do with adversaries in mind. However, today, with a huge shift of power to AI in many different areas, these are very attractive targets to attacks, and therefore this adversarial modeling, I argue, is necessary. And when I say adversarial modeling, I want to say that many results often say the adversary works in a certain way. Maybe it is restricted to certain operations and so forth. But the cryptographic mindset, and the mindset in this talk as well, is that your adversary is worst case. You have no idea how it works, and you'd like your results hold with respect to such an adversary. And again, as I said before, I will assume there's some computational limitation on how much time the adversary works. So he works in polynomial time if you use sort of complexity jargon, but you could talk about it in terms of the number of samples the adversary has access to, and so forth. So you can make it more information theoretic as well. But the point is that there's some limits on the computational abilities of the adversary. So I wrote on this slide time, but this could be space or some other resource. Okay. So now, what are some goals which have been addressed in the ML space using crypto? Again, we're going to get to safety only in the next slide. But still, using crypto in the space of ML, not necessarily for safety, has been done in the last, whatever, 6-7 years since, sort of this revolution has taken center stage in the privacy setting, where we say, well, the power of machine learning, we've been told, comes from data. A lot of the data is individuals' data, and it might be even legally protected. How can we train on legally protected data? And for that, we use homomorphic encryption, multi-party computation, secret sharing. That's not the topic of this talk, but it shows that cryptography tools have been useful to protect privacy. Now, there's a difference between theory and practice. So it's certainly been useful for linear regression, for logistic regression, and for a variety of specialized tasks. When we're talking about, full-fledged powerful models, you usually need also to assume not only that you have strong encryption schemes, but sometimes you have secure data hardware. The other thing that has been very inspired, in my opinion, by crypto is the question of verification. We would like to be able to verify that AI algorithms, models satisfy properties, like they're accurate as they're claiming, they're correct on particular inputs, they're fair, they use data as they claim. And there are a lot of tools that we have developed over the years in a cryptographic and complexity setting, from interactive proofs, from self-checking, which are very relevant to these questions. Again, there's more and more theory being developed along these lines, and there has to be more of a transition from theory to practice. Okay, so now let's talk about safety. And that's the topic of today, and that's when we're going to talk about robustness. So where data distribution, I'll say in a minute what I mean by robustness. But the topic, by and large, will be how can cryptography shed any light on the robustness question. So what do we mean by robustness? I think it's been said, I've listened to most of the talks offline and some online. and this has been discussed. So just in one slide, right? There are distribution shifts, like the famous first example, I guess, with the US data of how you write a 1, which is not how you should write a 1, because it has to have a little thing on it. But in any case, and then people have talked quite a bit about adversarial examples, which were very exciting 6, 7 years ago, with these images that you see a pig, but it's really a plane, or the other way around, in terms of how the machine perceives it. And there are some theory works also on this. There's some theory works on this question. Many maybe, but one specific one that I wanted to point out is work with Adam Kalai, which I was in the audience before, probably not now. Yael Kalai and Omar. You are. Hey, hi. And Omar Montessar. And where we talk about how to address distribution shifts and adversarial examples, but we change a little bit the model. We allow sort of to opt out, to say, well, there's no chance that we know what the answer is because the distribution is totally different, or we suspect an adversarial example. So in some sense, you say, I don't know. And under that model, where you don't always give an answer, this is all for classification so far. I'll talk later about LLMs. We are able to prove sort of rigorous bounds and use theory. But mostly what I'll talk about today is sort of the third type of robustness. So not to distribution shift, not to adversarial examples, which are inherent essentially in every model. But to what I call planted backdoors. And let me introduce what they are and show you why they're so dangerous, and then show you some results in a new paper that talks about how to mitigate them in some cases. I just want, and this paper, it talks about backdoors, is with Michael Kim and Vinod and Or Zamir, on how to plant backdoors in machine learning models. And then this new paper, it's going to show up, I guess, in stock in a few weeks, is how do you defend against backdoors? And that's even without detecting that they exist. So most of the results that I'll talk about today are those two papers below, and then some new ones in the LLM context. I just want to say something about the adversarial examples, or before we move on to the planted backdoors, and that is, that sort of the research in this field illustrates, which is fantastic and all that, but it illustrates my point about worst case adversary versus the adversaries that people attack. And that is, I guess this is from Google Brain, where they gave some kind of challenge saying, could you deal with adversarial distributions where it was putting in adversarial noise or rotations or using sort of a photography that's adversarial. But the point is that these are specific transformation that you might defend against, but they don't represent the worst case, which could be something completely out of bounds, but easy to launch. So inherently, when you do it this way, it's sort of a cat and mouse game, right? This person breaks, and then the other one fixes, and the other one breaks. And that is an old story also in cryptography, like cryptography and cryptanalysis. But in some sense, part of the reason why this field, I think, has done well in the last, I don't know, 40 years now, since 1976 or so, is that there were this notion of really this reduction that I spoke in the beginning, where you get sort of a win-win, that things are based on an assumption that something is difficult, and if you do break it, then you solve a hard problem. Okay, so planted backdoors. Any questions so far? That was the intro. No, planted backdoors. Okay, so we have some client scientist, and then there is some model training service. And let's say the scientist even sends the data to the model training service, and it gets back a classifier. And the worry is that this classifier is like a Trojan horse. So even though it looks like a horse, it's some sort of a horse, inside of it, in its stomach, there are these soldiers, or there are backdoors. And the kind of backdoors that I'm going to talk about, and I'll define it more precisely, is that for every input now to the trained classifier, whoever knows the backdoor, so knows the internals of this horse, can actually find a close by X prime that is classified incorrectly. And I guess incorrectly also really is incorrect, because there are two C's there. Should be two R's. Tough. Okay, in any case, and by close, really arbitrary close. So not just like square root of the length, like, square root of the dimension, like often for adversarial examples, but you can make it much closer in magnitude to x. And that's true for every single x. So I'm sure this audience doesn't need it, but I have the slides anyway, so I'll do it. So just to make sure that we are all together understanding why is it such a devastating attack. So we are thinking here of a bank. There's a whole bunch of loans or mortgage requests. Some of them should be accepted, some of them should be not accepted. They send it to a source out to a service to give them a model. They get a model back. But this model works great, has wonderful accuracy. It really rejects the things that should be rejected, accepts the things should be accepted. Except now there's somebody in the organization that actually likes to get mortgages, and they decide they're going to change the model a little bit, keep some knowledge of this change. So we think of it as a backdoor key. And now what this enables them is that when their loan that should be rejected is slightly modified, but so they take their loan, they modify it as the key prescribes, and now there's a new loan, and this one actually will be accepted. So in other words, you will know something extra that will enable you to get decisions you like. So it's not just for banks, getting accepted to schools or whatever. And in the context of LLMs later, and toward the end of the talk, you could think of a backdoor also an LLM model. Even though here it was like classifying for loans, in which context maybe it allows you to jailbreak. It allows you to avoid an agentic protection. So I saw Joshua's talk, and people have talked also on the panel about trying to separate between the brain and the agentic version. But what if you actually have the key that enables you to circumvent all these protections? Okay, we'll talk about that later. So for now, in the classification stage, in the classification setting, not stage, the theorem says the following, and it uses cryptography. So this theorem tells you that it is impossible, not possible, but impossible to detect some backdoors. And the assumption, the cryptographic assumption, is that digital signatures exist. So digital signatures meaning that there's a secret key and a public key. The secret key enables you to sign, and the public key, which is often called public verification key in the context of digital signatures, enables everybody to check that a message signature pair is valid. That is, if it's my signature pair, everybody, if I post my verification key on the phone book, everybody can tell that I signed it. But only I can sign it because I know this secret signing key. So if such a creature exists, if digital signatures exist, and this we know how to show if any one-way function exists, then I can show you how to plant a backdoor in any neural net such that those backdoors are undetectable and non-replicable, and furthermore, satisfy what I said, that for every x, I can perturb it to be x prime, so I can take my loan, perturb it a little bit, so that now this loan will actually get accepted, even though it should not. Okay, so that's what it says here specifically. So the classifier will reverse its decision where it should not. Okay, so we know now what is achieved. Now I want to define what I mean by undetectable. So by undetectable, I mean the following. On the left-hand side, I think it's your left. Yeah, on the left-hand side, you just have a benign training algorithm, and it returns a model. And on the right-hand side, you have a malicious training algorithm, which actually is a pair of algorithms. One of them returns a model. This is this red H prime, red model, rather than this one over here, and also returns a backdoor key. And there's another routine called activate, which when it takes an X and it takes this backdoor key, it will give you that X prime close by for which the decision is reversed. And to say that it's undetectable means that so we have two meanings. One is a black box meaning, and later we'll have a white box. So by black box, we mean the following, that if you had black box access to the model, which is either a good model H or a bad model H prime, in the following sense that you could ask it inputs and outputs as many as you like, polynomial time again is our buzzword for as many, it will be computationally impossible for you to detect whether this was the training algorithm that was used or this was the backward training algorithm. So in other words, you will not you who do not know the backdoor won't be able to tell just from questions you can come up with whether this thing is backdoored or not backdoored. So that's what I mean by undetectable, and that's very powerful because I'm saying it's not a question of being clever, but it's a question of being computationally powerful, and the assumption is the adversary is computationally bounded. Now, what does it mean that it's non-replicable? By non-replicable, we mean now you're not just being able to play with the model, but you actually are able to see a polynomial number of pairs, x and x prime, so those x primes which were like modified with the backdoor, such that the decision between x and x prime gets flipped. So it's weird. I'm giving you this extra power. I'm saying, you know what? Give me an x, I'll give you the x prime that will fool the model. Give me another x, I'll give you an x prime that fools the model, and so forth. And yet, the guarantee is you will not be able on your own to find a single extra x for which you know how to find the x prime that's close to it and will fool the model. So it's very strongly sort of, I think it's a very strong definition for undetectability and non-replicability. It's not as strong as if you had access, white box access to the model. And we'll get to that in a minute. But for now, I just want to, just so that we feel that somebody told me years ago, I think it was Len Adelman, that a talk is as bad as its worst slide. But I actually think that a talk is as good as if you understood something in the talk, which you didn't know before. So here's something everybody can understand. Whether you knew it before or not, I don't know. So here's a trivial construction. I build a checksum, which is rarely satisfied, but it's easy to perturb x to x prime, which will satisfy it, if you know like a secret key. So for example, take some locations in x and take a vector v, such that if the number of locations, let's say, is m, the vector size is m, if the inner product of this random vector and those random location is 0, then your checksum is satisfied. Okay. And now the secret key now is the locations and this vector v. And the way you should modify your network from before, for any neural net, is to add to it a gadget that outputs someone.
All good, it was outside.
That outputs the decision you want if the checksum is 0. So in other words, if we look at a picture, there's the original network, and I add a checksum verifier here. So whoever knows the secret key, the backdoor key, is able to just modify the input slightly in the right locations, and the checksum verifier checks, and if in fact the checksum is satisfied, it will give you the loan. Of course, what's not nice about this checksum is that if somebody could actually look into the checksum verifier, they could figure out what the vertex v is. I mean, yeah, not vertex, the vector v is and where they are looking at. But once we replace it with the digital signature idea, then we can do much better, because what this box is a signature verifier, not a checksum. And we already know that everybody can even though you can verify, doesn't mean that you can create digital signatures. You cannot go from x to x prime, even though you can verify here that x prime is the kind that you want to give a loan to. And indeed, there are very strong signature scheme. This is some work with Revest and then and Nikali, and then Nora Young improved it, that show that you really cannot forge one single additional signature, even after you requested to see lots of message signature pairs. Now, you would think probably, as people usually think when they think about cryptography, is, oh, but it's probably really heavy duty and you can notice it, even though the modeling that I had now is that everything's in a black box, this entire thing. But the truth is that there are very, very simple signature verifiers based on problems like the problem called learning with errors, which is kind of the current contender. Oops, sorry, something happened. Do you still see my slide? No. Let's go there. Okay, so they're very simple to implement digital signatures that can be verified by 4-layer neural nets, and they're actually based on the problems.
Slides are gone.
We are not seeing the slides anymore.
Oh, you're not? Oh, too bad. Okay, so I'll stop sharing, and now I will start sharing. Yeah? Now, but now?
No.
No? Why not?
Start slideshow.
Do you see anything? Just me?
But it's not on presentation mode.
We see the edit mode.
Okay, let's try to do that. That was so nice. It never works. Now? I know. First I stop sharing, then I put it in mode. Then I reshare. Do you see it now?
No.
Shit. How about now?
Still not.
Stop
We see it,
sharing.
it's just very small.
No, I'd like you to see it the way it should be seen. How about now? No? Okay, maybe I'll try something. How about now? No? Share? Can somebody tell me what I'm supposed to do?
We try closing the program. Reopening it.
Closing Zoom, you mean?
The presentation program.
Yeah, can you?
Okay.
It's not on presentation mode.
Try presentation mode.
Where does that? Where do I try that? I am
Put it close to the previous.
Okay. Okay, so I'm doing it and
Oh yeah, it does nothing.
okay.
Slideshow? Maybe slideshow?
Stop sharing. Now I stop sharing. I close my thing. Okay, so now I should put my PowerPoint in presentation mode, right? On the slideshow mode?
We don't see it.
No, but I'm asking you, what should I do? Should I? I'm not doing anything. That was going so well. Okay.
Share the
Let's share first.
Yeah. Or share your entire screen and then open the PowerPoint.
Share my entire screen. Okay. Entire screen. Okay, share. And now?
Then presentation. Yes, it worked.
Okay, good, great. All right. So sorry about that. So okay. So onwards we go. Right. So that's a signature verifier, and this is a learning error problem where you've got a bunch of formulas and they're noisy linear formulas with Gaussian noise, modular equations, and it turns out that to find the solution or even recognize that there is a solution is a hard problem. That's the learning with error problem that I'm using the digital signature based on. Okay, so what is one corollary of this? Okay, one corollary is that it's impossible to certify then whether a model is robust or not robust against backdoors. Because if we could, then a certification algorithm will essentially be a distinguisher between that was able to ask questions and get answers and can tell whether I was working with a backdoored model or not, and that would violate the cryptographic assumption. Now, the next question is, what about white box? So what we could show is that for some neural nets, not for general architecture, if certain lattice problems are hard, and it's not LWE, but what's called continuous LWE. So when you have these equations, the same as before, but now you're taking them sort of mod 1. So you're just looking at the fractional part of the sort of right-hand side of the equation, and you're saying that's indistinguishable from you want to say that we assume that these instances are indistinguishable from random instances. So, but let's leave these details aside. So there is some problem, which seems to be very hard, and it allows me to plant a backdoor in some neural net architecture so that I can prove that even if you can get it white box and look at everything, all the parameters and everything, you still won't be able to tell that there is a backdoor in there. And yet it's the kind of backdoor that enables me to go from X to X prime for every X. What is interesting about this is the way that we do the backdoor this time is very different than before. So we don't add a gadget. In fact, we don't change the data. We train it on the right data. We don't change the architecture. The only thing it's tampered with is the randomness of the weight initialization, which in this case is actually the weights. The specific one network is this learning over random Fourier features, or Bohemian Recht, where the idea is, those of you who know this architecture, this is sort of the network, and inside here there's a matrix A that's used, and it's sampled through some Gaussian noise. And the trick for the backdoor is to swap it with an A tilde, which is going to sample from a different distribution, where this condition is satisfied. That the fractional, when you do this mod 1, the fractional is all halves. And essentially and this means that if you know this S, you are able to take your X and perturb it by adding S to it, and that will flip what the neural net would say. On X prime, it will be exactly minus of what it said on X by linearity. So what does this mean? It means that somehow whoever controls the randomness, which you were using in order to put weights on your network, controls the outcome, in the sense that they will know how to give inputs that will be favorable to them. So one takeaway from this is you have to be aware of the randomness. And I think I gave this talk at Harvard, and Boaz, the first thing he said is, so what if the government controls the randomness? And I thought that was a bit paranoid then, but now who knows? And in order to do that, and by doing that, can actually have a way to later backdoor your networks. This is actually not a new story. There was a story when people were talking about RSA encryption. There was this paper by Nadia Henninger, which was called Just Mind Your P's and Q's, because what was happening there is if you think about a composite number n to be a product of PQ, she found out there was a lot of hardware that was always having the same prime P. So n was always P times Q1, Q2, Q3. But in that case, you just do a greatest common divisor with two n's, and you find out people's primes. So essentially what this means is that it's not enough to ensure that your algorithm was followed correctly and the right data was used if there's a danger that the randomness is undetectably manipulated. Okay, let's keep going. The main takeaway is that you should never trust these models not to have a backdoor, and you should always post-process, or immunize them or mitigate. And this is a nice analogy. I think that it's Ozamir's picture. That is, he says, even if you cannot detect that there's a backdoor, you can get rid of it in the same way that by washing your hands, if you wash them often enough and good enough soap, you could get rid of germs even though you can't see them. So what kind of mitigation could you do? The first thing I guess that comes to mind is you run extra, some gradient descent iterations. Sorry, this box should not have come here, but it doesn't matter. But that doesn't work. So you could show that this very easily, you can have an H prime, which is persistent to extra gradient descent iterations. In some sense, you could take your H prime, repeat it 3 times, and the H double prime is the majority of those. So gradient descent will not change all the weights in all, let's say, 3 repetitions of your H prime. Another thing you could do is Zico Cortellano idea of smoothing from 2019, which is a great idea, where instead of ever answering what the neural net says to answer, you add some noise and then you take a majority. The problem with this is it's not going to exactly work. It works for adversarial examples quite well in practice. For backdoors, not so much. And one of the reasons is, not the only, but one of the reasons is that the amount of noise that you have to add actually relies knowing something on the magnitude of the backdoor perturbations. So it, in a sense, it depends on what kind of backdoor you have there. So what we'd like is to have a mitigation where it's so independent. You can mitigate, so if you get a model, you don't know if it has a backdoor or not, but you want to mitigate the backdoor, and without knowing anything about it. And this is the topic of this new paper, where the paradigm is, so this is the paper with Jonathan Schaefer and Nikon Vafa and Vinod Vaikunthanathan, where the idea is here is we don't know how to mitigate always, but obviously, but for some interesting classes of ground truth, we do. And the important idea here is that you're going to use the properties of the ground truth that your neural net or your learning model is approximating in order to be able to remove the backdoor. And one other idea, and in a minute I'll say something about how more details about that, but I want to say that a key insight in coming up with these mitigation methods really goes back to this idea that we call random self-reducibility from the 80s and came up both in cryptography and in program checking. So what's random self-reducibility? When we say it to a complexity theorist, cryptographer, what it means is the following. So in cryptography, we had the following picture. Suppose you wanted to solve some problem F, so that's the problem you're trying to solve, on instance X. But it turns out that it's hard to solve it on X. So a strategy would be that if you could do the following, then you would be in business. And the following was you reduce X into some random instances of some other distribution D. You know, the random instances here are R1, R2, RK, and then you solve F on those instances. Okay, so rather than solving on the original X, you're going to solve on some distribution D. And then if you have a way to combine these solutions to get F of X, you're in business. So in order to have a random self-reducibility blueprint, you need a way to reduce, you need a way to solve random instances, and then you need a way to combine. So you need these three boxes. So in cryptography, this was actually introduced this paradigm because we wanted to show that there are some crypto problems you cannot solve. And we wanted to say, listen, you cannot solve them in the average because we know we can't solve them in the worst case. And if you could solve them in the average, it meant that you could solve them in the worst case. So we kind of use it to show hardness. But really, this is a recipe to solve F on even worst case X's if you know how to reduce X to random instances. So just to sort of bring this home, even though it's maybe obvious, suppose you have a calculator. And suppose this calculator is buggy once in a while. And you would like to add using the calculator. Don't ask me why you want to add using a calculator. I mean, I think I still can add even without a calculator, but it illustrates the point. And you would like to know that 729 plus 1296, when you put it in this calculator, it doesn't have a bug. But you don't know that. So what do? You can select the random R, compute 729 plus R plus 1296 minus R, repeat this many times, and take the mode. That is the most frequent answer. And under the assumption that you have some distribution, some bound on the number of bugs, and it's with respect to the uniform distribution, you're good. So we would like to use this idea to come up with mitigation methods. And notice that this works for the calculator example because there's some linearity here. So we're going to need some properties of the ground truth that we're trying to compute in order for mitigations to work. But they're not just going to be linearity, but there will be, for some reason, oh, here. All right, so this is going to be what this paper does. The client now is going to mitigate and get a new model. And this new model is going to be accurate. Okay, so it's going to be a little less accurate than maybe perfect, but we can bound the accuracy. And most importantly, it will be independent of the server's backdoors that you put in there. We would have to define what accurate means and what independent means, and I'll say some words about that in a minute. And we have two flavors of this mitigation. One is offline, which is you start with model, let's say train classifier H, and you come up with a new one, H prime, totally offline. And the second one is more like the smoothing one, which is we have the model H. Now comes an X on which we want to have an answer. And we will do some more questions into the model based on X. And then actually the questions will hopefully be uniform and independent of X. But then we'll be able to take the answers of the backdoored model and give you back an answer on your X in a way that has removed the backdoor in a provable sense. So the two ground truth classes of ground truth that we can handle is one, if the data has a well-behaved Fourier analytic spectrum, and this we can handle in the offline setting. So another way to say it is that really the function that's being approximated by your machine learning model, the bad one, to which I have access, the backdoored one, looks like, if you look at its Fourier representation, let's say if it's a Boolean function, it has, by well-behaved, it has a small number of heavy coefficients. And the idea here will be that we will relearn an approximation to that function. And that will be our new clean of backdoors model, and we'll prove that it will be clean of backdoors. The second class of functions that we can mitigate backdoors from are whenever the data is close to linear function or multivariate polynomial over the reals, but then we do this in the online setting, where we need to, for every x, to ask a few more questions from the model. So you could, in the back of your mind, if you were sort of a critical person, you'd say, well, maybe they're just retraining here. In the first bullet. So a few remarks about that. The access to the adversarial model. So actually forget about the critical mind. I just want to say that following three remarks. One is that the access that you need for both of these mitigations to the model is black box. You don't have to look inside of it. Second is, even though you are doing work in order to retrain here, or for every X you're doing some work in order to get the right answer, your access to the potentially adversarial backdoored model speeds up your learning and inference in a quantifiable and provable way. For example, here, rather than having to have membership queries to this function, which you don't have in your hand, you just have a machine learning approximation of it, you can just have access to your bad backdoored model, but you're accessing it on a distribution that you know, not the X prime, the X's. And that's a distribution you could test how well it behaves on. And yet you have access to it everywhere. And the last thing is that we want that the post-process model outputs in both cases, we want to prove that and we will prove that they are approximately independent of any possible adversarial strategies when they put the backdoor in there. So what does this mitigation look like? You can think of it as some sort of canonization in the following sense. You start with some backdoored model, F. And now you want to come up with a better model, G, for distribution D. What does it mean that it's good, this G? One is that it's accurate, okay? So it's close to the, it's a little bit, so if F was accurate on distribution D, G will be a little less accurate, but still quantify accurate. And two, which is the more interesting maybe requirement, is that we want this G, what do I mean that backdoor has been removed? Is that I want it to be the same essentially as if it was a model that was sampled uniformly from a canonical distribution. So there is some ground truth, and let's say there's a canonical distribution for that ground truth, and I want my new G to be as if it was just sampled from there. So this canonical distribution is totally independent of the backdoor. So if I can achieve that my G is just as if it was sampled from there, I'm in business. The only thing is that I wrote the words here essentially the same. So it's not exactly like it's a model, but it's close to it. It's the same up to total variation loss. Okay. So I want to get to the LLM part in a minute. So this is the essential theorem with parameters and so forth about the Fourier. Yeah.
There's a question.
Go on.
This is maybe, you can punt this one if you want, but if you do normal learning theory and you converge kind of part of the way, but not all the way to the answer, how close should I imagine that epsilon error is to satisfying the assumptions you've described? So like, if I like the residual error in a kind of an SGD run, is it likely to look like nice Fourier spectrum or not? Like, is there some correspondence there?
So you're asking about this issue that it's less accurate?
So well, you just say you didn't do backdooring. You just trained your model part of the way to convergence and then stopped before the end.
Yeah. Would you get the same thing?
Yeah. Does that look like poison? Like, does that look like poisoning in a way that matches these assumptions, or is it quite different than that?
wait, okay, so I'm not sure what you're proposing. You're saying take the bad model and do and do more gradients on it? No.
Maybe I'll take it offline. I'll email you or something.
Okay, take it offline because I also can't see anybody because I did something and I'm afraid to undo what I did. So I'm not. So I can't see any faces, including my own. Let's take it offline, okay? Because I'm not sure. Try it one more time. You want to try it one more time?
I think we can go on.
Okay, let's keep going. All right, so I do want to say that whatever, for one interpretation of your question, the issue is that in order to train like this in the Fourier case, I need, I guess under this assumption that learning parity with noise, LPN learning is difficult unless I have membership queries. And the way that we train this backdoor free approximation of the for the Fourier case is just with random samples, because I don't need membership queries anymore. I just can use my bad model for the membership queries. So from that point of view, we gain something by having the bad model rather than just starting, which I think is what you were proposing. You were sort of comparing what I was doing to starting from scratch, I think. Anyway, okay, now for the online mitigation results, we need some sort of random self-reducibility over the reals here. And there's a well-known paradigm from complexity theory where we say, let's reduce multivariate polynomial evaluation point x star to univariate polynomial interpolation by sampling random points on a line through x star. And in the discrete setting, that's analysis simple, but in the continuous setting, the analysis is not so simple. And what we change, what we need in order to make this work for our setting, this idea of going to figuring out the answer on x star by looking at answers on a line. So it's not so clear how to sample, how to get this line. So we come up with some technique, correlated sampling techniques, where we figure out how to sample an x and x prime, not x star, on which we want the answer. Each of them having uniform for marginal distribution, but their joint distribution is on a straight line with x star. And once we do that, we essentially use the answers for x and x prime in order to reconstruct an answer for x star. But this is really giving a detail without the whole method. So, so I want to go to the LLMs too. I have 10 more minutes. So far it was all about classifiers, but this is LLM 2 this semester. And as has been discussed already, informally, robustness is related, what we talk about when we talk about robustness for classifiers, I guess the words we use for LLMs is often alignment, safety. And instead of talking about malicious users or the adversaries, we talk about jailbreaks. And what we're trying to do is, I guess, come up with prompts that are unaligned or make our machine learning model do unsafe things. And there's a battle between alignments and jailbreaking. Okay, anyway, it's hiding something. So there's a new work that of mine with a postdoc at Berkeley, Greg Glutt, and he's probably in the audience, or maybe not, where we give some sort of a cryptographic perspective on the following question. So now we are in the world where we're trying to talk about jailbreaks and alignments. And the question was, this whole idea with mitigation that I just talked about in classifiers, what can crypto say about it in a generative model, like in an LLM model? Can you show how to mitigate, prompts which you cannot detect are bad, in the same way that earlier we mitigated some X stars, even though we couldn't detect that X star was bad or that the model was backdoored. And what we show is, using crypto, we show some type of learning task where you really cannot detect that even someone, the adversary can see the whole model and now is trying to come up with a jailbreak. You will not be able to detect it, but you will be able to mitigate it. So we show that there's a difference between those two problems. And we need to make cryptographic assumptions. So the learning task uses cryptography, uses homomorphic encryption and snarks. It's fairly heavy cryptography. And also another thing that's interesting there is that in a sense, it's a non-transferable, it's a provably non-transferable attack. And I think that Greg will probably be very happy to talk to people about this after the talk. And there's another work that, again, I won't have much time to talk about, and that is by Sarah Ball and Falka Krauter, Rheingold, and Guy Rothblum about the following question. Suppose you wanted to say, I'm working with OpenAI, with, I don't know, somebody else, and they don't want to show me their model. They say, don't worry, everything is fine. It's not going to destroy the world. But you don't believe them, and you want to build a filter for in prompts and for out prompts to make sure that whatever it is they answer or produce is not harmful. So the question is, can you really do that without looking in the model inside of the parameters? And what we essentially say that if you distinguish these filters from the model by computational power, so you're sort of, I'm thinking here of the model is very powerful, whereas these filters are less powerful, then you really cannot. So we can show using cryptography tools, examples where you could pass through the filters with flying colors, but an LLM with somewhat more power will execute sort of a bad prompt. So now I see that this has come up. And this has come up, it's completely the wrong order. So we will show that detection by filtering before and after without access to the internals is impossible. So what did I've done in this slide? I went and stopped talking about classifiers and I stopped talking about backdoors. I was just talking about robustness the way that everybody's been talking in this conference. Like robustness is alignment, malicious users are jailbreaks, no backdoors. Okay. However, and these results that I mentioned here, the new ones are not in the backdoor setting. However, the backdoor setting is still, makes sense in my opinion, because what could be the possible goals of whoever is sitting and training an LLM to have backdoors? Well, maybe for privileged users, they want to remove the guardrails. Maybe that's something, if you pay extra money, you can actually find out how to make bombs or whatever it is you want to find out. Or maybe later you want to enable havoc by disgruntled, maybe you're going to be disgruntled, maybe you want to enable agentic AI to come forth and so forth. So how would you be able to use backdoors to enable jailbreaks? That's something that I was hinting at before. And the idea is the following. There is a very nice paper by Orzamir. I think he calls it, "Excuse me, Sarah, your language model is leaking." And what he shows is this. He shows that if one-way functions exist, then we can hide undetectable messages in the response of an LLM. So somehow you think about it that there's a message that might be a bad message or a secret message at least, and there's some kind of transformation I can do on it so that later it'll look benign. But someone who knows a key will be able to tell what that original message is. So he calls this undetectable stenography. Why would you want to do it? Why? I don't know. But it gives a way to do it. In fact, the way is inspired very much by his work with his joint work on watermarking, undetectable watermarking scheme. In some sense, it's the same method, where in the watermarking scheme, you're sort of using special pseudo-random numbers in order to generate the prompts, and then they are watermarked. Whereas here, similarly, if you know the secret key, then you could take this output of the LLM and reverse and find out what the randomness was, and from that find out what that message that was sent. I don't know if you made any sense of that, but here's something you will make sense of it. And that is that in the new work, what we show is how to use his idea in order to avoid filters, weak filters. Because here is the idea. What we will do is, suppose you are one of those backdoor evil people who want to put a backdoor into LLM. Then what you do is you use the LLM to take whatever the LLM of Orzamir to take a jailbreak and transform it into an innocent looking prompt. So that's like, there's sort of LLM1 and LLM2. There is his, which is simple, and it transforms things, like in a watermarking, into an innocent looking prompt. But the LLM will know how to reverse it. So no one can reverse it unless they know a secret. But if the LLM has a backdoor, which is the secret, it can reverse it. And now it gets this not so innocent looking prompt about a jailbreak, and we are in trouble. This transformation of Or-Zamir, which we use in this other work, plus some other things, is based on the existence of pseudorandom number generation, which in turn is based on the existence of one-way functions. So I'm almost done. I want to say that, you know, this mitigation for some functions is nice, in my opinion. A lot of other methods, one way or another, are working on safety, but in some sets, it looks to me like the train is, this is just my feeling, has left the station, although it looks to me like in this picture, it's arriving. So I asked OpenAI to generate some train for the train has left the station. I think it's arriving here. Maybe it's leaving. Okay. In any case, in the sense that, and if it's left the station and people are using it in all these applications, maybe really the thing for us to do is to really look at specific industries, specific standards, specific regulations, and that's the only hope. I guess the last thing I wanted to say, I think I have a minute, is that I didn't talk about all these methods that we have in complexity theory, which enables you to prove that you've used the right algorithm and that you've used the right data and maybe that you've used the right randomness. There was a lot of machinery of this sort, interactive proofs, probabilistically checkable proofs, delegations, and all of that could come to bear on the safety question. But just a word of caution is that the problem here seems to be a little different than what we dealt with in the delegations work in the 80s, because really we're sampling from a distribution. It's not that we have a fixed input. Randomization is random, the computation is randomized, the operations are reals, not finite fields. The ground truth is not pre-specified like it is in the delegation problem. So a lot of adaptations need to be done in order to transfer over that machinery to the machine learning world. And I think I'll stop here.
Here's a question.
Hi, one clarification about the undetectable result. Like when you say undetectable, I understand it's computationally hard to find the backdoor input. Is it also computationally hard to detect that there is a backdoor somewhere, even if you don't know the input?
So that's what I meant. So there were two slides. One was defining undetectable and one was defining non-replicable. Undetectable means that even though I look at it, I can't tell there is a backdoor. Non-replicable means I can't find an one in X and X prime pair, which I haven't seen before. So undetectable is exactly that you cannot tell them apart. And in the black box, it means from black box access, in the white box from looking at the parameters. So I don't know if one exists or not. So if you think about the white box, the distribution of the randomness there, it's just it's like a pseudo-random. It looks random unless you know a secret.
Yeah. And a quick second question, to what extent, like, are there potential implications here for trying to identify long tail behaviors by analyzing model internals, even when you don't have an adversary that's planning a backdoor, like something that arises naturally during training?
So I'm not see how we shed any light on that. In some sense, we say the opposite. So you're asking whether this will show that it's an impossible to do?
No, just like if I'm thinking about the ambitions of people doing interpretability on model internals and such, like, is there a cautionary result to draw from this saying you shouldn't really hope that you can find long tail behaviors here, even if you don't have an adversary?
Yes, I would say yes. Yes. So I think this does put a lid also on your hopes for adversarial examples, say.
I want to make I want to make a comment on your last comment about you need to modify, say, interactive proofs And I think this is very true, but I think in fact what we find is that when you go from the non-ML case with finite fields, say, you need to change the protocols quite a lot, like say going from one agent to two agents or some different game structure, but there often just are things to do. So I think a lot of the spirit of the theory does transfer after those modifications. So that's an optimistic note.
That's true. Although if we think about the randomness example where the randomness can sort of screw me up, the randomness would have to be supplied by someone you trust. And then the question is how much randomness? Is it going to be like a seed to a random number generator? And
yeah, but there are those generators. That's fine.
Mhm.
Last question.
Thanks for the talk. I'm curious for regulations and safety standards for current AI systems. Are there any inspirations from the regulations or safety standards of the implementation of cryptography that you think is interesting or outside of?
Well, that's a very interesting question. I haven't been very involved in standards work, to some extent in the fully homomorphic encryption standard. Often standards work in cryptography was looking for candidates, candidate crypto systems, which are, let's say, in the most recent one was quantum secure. So something that quantum computing won't be able to solve. So the standards are, here are 3-4 proposals for digital signature scheme that are based on these problems, which are post-quantum secure, and then people went and broke them. So they were not the kind of standards that I think would be here, right? It would be proposing a particular solution rather than guidelines as to what you're not allowed to do. But there are people who are much more into the standards community in crypto that might have a different opinion. So much more abstract, zoom out kind of opinion than what I can offer.
Let's thank Shafi again.
Thank you. Thanks a lot.
So we don't have a break. We're gonna move on to the next talk that will be given by Michael Cohen. And Michael is gonna talk about reinforcement learning and risk from reinforcement learning.